There is another problem. Hot oil is to be cooled in a double tube counterflow heat exchanger. The copper inner tubes have a diameter of 2 cm and negligible thickness. The inner diameter of the outer tube, the shell, is 3 cm. Water flows through the tube at a rate of 0.5 kg per second and the oil through the shell at a rate of 0.8 kg per second. Taking the average temperatures of the water and the oil to be 45 degrees Celsius and 80 degrees Celsius respectively. Determine the overall heat transfer coefficient of this heat exchanger. There is a figure having all this data from this question. Hot oil comes from this and cold water comes from this. 2 cm, 3 cm, 0.5 kg per second and 0.8 kg per second. So this is all the information we have received from our question. To solve this particular question, we need this property table. This is a property table of properties of saturated water. Here, from this we can know temperature, saturation pressure, density for liquid and vapor, enthalpy of vaporization, specific heat for liquid and vapor, thermal conductivity for liquid and vapor, dynamic viscosity for liquid and vapor, Prandtl number, liquid and vapor, and volume expansion coefficient beta for liquid only. We need another property table, and this one is properties of liquids. And from this property table we can know temperature, density, specific heat, thermal conductivity, thermal diffusivity, dynamic viscosity, kinematic viscosity, Prandtl number, and volume expansion coefficient beta. So to solve this particular question, we need this two property table. For fully developed turbulent flow, the more accurate Nusselt number can be calculated from the Dietz-Boelter equation. This is the equation. Nu, that means Nusselt number, is equal to 0.023 Reynolds number to the power 0.8 Prandtl number to the power n. Re greater than 10,000 and 0.7 less than equal Prandtl number less than 160, and n is equal to 0.4 for heating and 0.3 for cooling. Flow through tube annulus. Tube, and this one is annulus. Di, do, so inner diameter, outer diameter. ds is equal to 4ac divided by p, that means 4 pi. AC means pi into d naught square, do square minus di square divided by 4, and p pi into do plus di, that means do minus di, because 4 pi and do plus di into do minus di, so do plus do plus di all are vanish, only there are do minus di. Annular flow is associated with two Nusselt numbers, NUy on the inner tube surface and NUO on the outer tube surface, since it may involve heat transfer on both surfaces. So you can write NUy is equal to HI ds divided by K, and NUO is equal to HO ds divided by K. The Nusselt numbers for fully developed laminar flow with one surface isothermal and the other adiabatic are given in table. Nusselt numbers for fully developed laminar flow in an annulus with one surface isothermal and the other adiabatic. Keisen, Perkins, reference 40. So when d inner divided by d outer is equal to 0, there is no inner Nusselt number and outer Nusselt number is 3.66. When d inner divided by d outer is equal to 0.05, the inner Nusselt number 17.46, outer Nusselt number 4.06. When di by do is equal to 0.10, inner Nusselt number 11.56, outer Nusselt number 4.11. Like that, for 0.25, inner Nusselt number 7.37, outer Nusselt number 4.23. For 0.50, inner Nusselt number 5.74, outer Nusselt number 4.43. The last one for 1, inner Nusselt number 4.86 and outer Nusselt number 4.86. So from this table, we can say that after increasing the value of d inner by d outer, Nusselt number for inner decreasing and Nusselt number for outer always increasing. And we can find some other values from this, like when d inner divided by d outer is equal to 0.40. So this one is between this 0.25 and 0.50. We can easily find them from this table by interpolation method.